Alright, this video is going to help us with the concept of what's called a series. Now we've talked about sequences before, so let's review that very quickly because a sequence is going to help us out when it comes to finding a series. A sequence, remember, is just a pattern of numbers, such as the pattern on top here. A sub I is equal to 3i minus 1. Now a lot of times we use n, here they happen to use I, it's just a variable. But remember, if it's a sub 1, well that means I was 1. We're going to plug 1 in for I up here. So 3 times 1 minus 1, and a sub 1 is equal to 2. Now you'll notice I've filled in all the other numbers up here as well. So we've got the terms 1 through 5. Again, it's sort of a linear pattern. We've got that 3 times I minus 1, which means we went up by 3's, 2, 5, 8, 11, and 14. We've got all of our terms worked out. Now the difference between a series and a sequence is the series is actually going to take all the terms of the sequence and add them up. Right? We're going to add up those terms. So you'll notice down here at the bottom we've got what we call sigma notation or summation notation. Series can also often be called summations. Right? So we've got this Greek letter sigma in the middle. It's this capital sort of E looking thing. And again, when you write that out, you've got to try to draw it as accurately as you can. It's not actually a capital E. It's just sort of that zigzagged figure there. But again, the idea is this. That's really the symbol for summation. So instead of having 5 separate terms, what we want to do is take all the terms and add them up. So I'm going to find a sub 1, 2, 3, 4, and 5, because notice it says to start when I is 1, and basically work my way up. Again, I is 1 being my lower limit, my first number I'm going to use, or when the index, as we call it, there's why they called it I, when the index starts from 1 and it works our way up to ending at 5, the lower limit being 1, the upper limit being 5. I want terms 1 through 5. But again, really the only twist to this whole thing, after I've plugged in my 1, obviously I'm going to get 2, plug in 2, I'm going to get my 5, then we'll get 8 and 11 and 14. So basically we're going to get all the same numbers down here that we just got up top. Only now it's the summation of. I want to add up those numbers. Basically, if we take 2 plus 5 is 7, makes 15, plus 11 to be 26, plus 14, we're going to end up with 40. And the sum of the terms from 1 to 5 of the sequence, 3i minus 1, would be equal to 40. We're just going to get one answer because, again, we're not just finding the terms of the sequence. We're adding them up. So let's go ahead and try that. Let's take a look at this sequence, or series, I should say, that we have up top here. The summation looks like we're going from term 1 up to term 4. So we should have 4 terms. But now notice we also have basically what looks like a quadratic function in there, quadratic expression. So I'm going to have to plug I into a couple of different spots. We're going to get quite a few terms. And in fact, feel free to try that if you want to. I'm going to reveal the answer in just a second. In fact, if we plug in 1 for I, again, we'll get 1 squared plus 2 times 1 minus 3. Again, that would be term 1. That's a sub 1 when we're talking about the terms of the sequence. But again, we're going to add that up. It's a summation or a series to plugging in 2. And plugging in 3 and plugging in 4. If we find all of those numbers, notice we've got them nicely color-coded for you there, we'd end up with 38. Now realize, since all we're really doing is adding up all of these different terms, these extra parentheses in here really aren't doing a lot of good. I could have added up 1 squared and 2 squared and 3 squared and 4 squared, because really it's just addition. We can use the commutative property. We can add in whatever order we want. So we could really do all the x squared terms, then do all the I to the first terms, or I squared terms I should say, and then I to the first terms, and then do all the constant terms. We could separate out all these parts. Or basically, when you have a summation of things that are added together, you can separate them out. The sum of 2 terms that are added is really the sum of the first term plus the sum of all of the second terms. Now, in that same way, well, hey, if it's 2 times every one of these terms, well, can't we just use a little bit of a factoring property? If every one of those terms has a 2 in it, right, inside of it, couldn't I just pull that 2 out? Again, 1 plus 2 plus 3 plus 4, and hey, we want to take them all times 2, right down here. So again, we also have another rule that says if there's a multiplication going on inside of the sum, then you can factor out that 3, or you can factor out that coefficient. Let's find the sum of the first 4 terms, 1 plus 2 plus 3 plus 4, right? Plugging them in for I. Then we'll multiply by 3. We'll just factor out that number, right? Like we did over here. Let's factor that thing out. Finally, there is one more really helpful shortcut for this summation. If the last term is all going to be negative 3's, well, hey, that's just saying when I plug in 1, there's no variable to plug in for. It's really just a negative 3 plus another negative 3 and another negative 3 and another negative 3. We've just got 4 different negative 3's, right, or subtracted 3's in our formula. Well, if that's the case, there's really just 4 of them. If you have the sum of a constant for I equals 1 to n, so we've got n terms in the sequence, right, in the series, but if they're all just 3's, well, I can just take 3 times how many there are, kind of like we took our negative 3 right here, times how many there were. Negative 3 times 4 becomes negative 12, and we still get 30 plus 20 minus 12. We still get 38. We get the same answer we got last time. So again, take advantage of those nice 3 shortcuts there. Maybe they'll save you some time when you're doing your homework. There's nothing bad about doing the sequence the long way, doing the series, I should say, the long way, finding all those terms, then adding them up. But again, if we can sort of chop it into parts and maybe take advantage of a couple of shortcuts, such as these, maybe we can save ourselves some time. Speaking of time, though, it's time to try a few extra examples. So think about what we've just learned about a series. See if you can't find the answers to the 3 series on the screen here. Pause the video now. I'll fill in the answers, and we can see them in just a second. Okay, so we're ready to take a look at the answers here. Hopefully the one in the upper left wasn't too difficult. I went ahead and took advantage of that simple shortcut. Since there was a 3 multiplied by I squared, I went ahead and moved the 3 out in front. I found my 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, right? First 5 terms of I squared, plugging in 1 through 5. We calculated all those squares, added them all up, and multiplied by 3 at the very end, and got 165. Then down at the bottom, same thing. I took advantage of our constant shortcut. There are 4 terms, I from 1 to 4, right? When I went to plug in 1, though, there's nowhere to plug it in. My first term would have been a 6. My second term would have been a 6. My third term would have been a 6. My last term would have been a 6. Basically, I had 4 terms of 6, and we would get 24. If they talk about a partial sum, the idea there is they had given us an infinite sum, but a partial sum means if it's the third partial, I only want the first 3 terms. So I'm going to do terms 1 through 3. So notice I ended up with 2/3, 2/9, and 2/27 when I plugged in 1, 2, and 3 up there in that exponent. Well, when I added those up, my calculator gave me an approximate decimal, right? This was approximately 0.963. But I went ahead and used my arrow to fraction button, right? If you remember on your calculator under the math menu, you've got that first option in arrow to fraction. And if you hit that button, it'll give us back that 26 over 27. And then finally, this one was a little bit tricky. It said I wanted to go 1 to infinity. Well, I don't have time to calculate an infinite number of terms. But if you notice, your first term was 3/10, then 3/100, then 3/1000, written in decimal form, 0.3, 0.03, 0.003. Add them all up, we're basically getting 0.3 repeating. And since I know 0.3 repeating is really equal to 1/3, I went ahead and got a final answer of 1/3. Hopefully those help you with some of those series that you'll be working with tonight. Make sure if you have any questions that you talk to your teacher. I'm also going to give you a quick overview in this video, just because dealing with sequences and series, sometimes we deal with factorials. A couple of hints about dealing with factorials here. So if you're ready to go and you think you can do your homework, I'd say go for it. But otherwise, here are just a couple tips about dealing with factorials. When you want to deal with the 5th term of this sequence up top here, a sub n equals n factorial over n minus 1 factorial. If I'm plugging in 5, basically what I'm going to get for a sub 5 is 5 factorial over, well, 5 minus 1 would be 4 factorial. Well, that's really 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. So oftentimes what I'll do is I'll take a look at my fraction and say, well, if this is 5 and everything below it, and 4 and everything below it, well, the forward and down basically lines up. So rather than writing that all out, what I'll usually write is 5 times 4 factorial, the remaining terms, right, 4, 3, 2, 1, over 4 factorial, which means the 4 factorials cancel, and we just get 5. Well, let's find the 10th term of the sequence. Again, a sub 10 would be 10 factorial over 10 minus 1 is 9 factorial. Well, rather than writing that all out, that's 10 times 9 times everything below it over 9 times everything below it. Again, we're going to get that 9 factorial to cancel away. And very simply, we'll just end up with 10. Well, let's simplify the sequence. That means that this is really n times n minus 1 and everything below it over n minus 1 and everything below it. So you'll notice, again, there would be y, makes sense. N minus 1 factorial and n minus 1 factorial, that would be y for a sub n. We just keep getting back n, whichever term we're looking for. So that's kind of nice. Now what that can do for us is, over here for our series, when I go to plug in 2, well, I know that a sub 2 is really just equal to 2. And I'm going to add that on, right, to a sub 3, and a sub 4, and a sub 5, and a sub 6. Notice we're stopping at 6 here. Well, really, I don't need to do all this factorial work. I already know a few things. So 2 plus, well, if it's a sub 3, it was 3, and 4, and 5, and 6. And 5 plus 5 would have been 10, plus 4 and 6 is another 10. I'm pretty sure, taking that nice shortcut, I'm just going to get 20. Again, that's a great way to cancel off factorials. Remember, you're counting from the number you have down to 1. So when that starts lining up with the numbers in the denominator, we can start getting rid of, right? Rather than writing them all out, we could start getting rid of these 4s and 3s and 2s and 1s, or we can get rid of it altogether, right? Much like we did with that 9. Get rid of those altogether. I hope that helps you thinking about factorials. If you have any questions, again, talk to your teacher. Otherwise, have a great day.